Chapter 11 Approaches and Landings. Introduction. Approaches and landings are critical maneuvers and require the skills built from basic flight maneuvers, ground reference maneuvers, and airport traffic patterns. A proper approach is required for a proper roundout and touchdown. With a large number of environmental variables the pilot must consider, in addition to the skill to judge aircraft speed, descent rate, and distance above the ground, landing is normally the last basic maneuver the student learns before solo. Approaches and landings will be faa-h-8083-5 discussed with the fundamentals of a normal approach and landing in calm winds on a large hard-surfaced runway. This will provide the basis for specific power-on, crosswind, and steep approach maneuvers, as well as other types of approaches and landings that WSC commonly encounter. Normal, calm wind, approaches and landings. A normal or regular approach and landing involves the use of procedures for what is considered a simple situation. It provides the minimum number of variables for the student pilot to learn during the faa-h-8083 landings, that is, when engine power is at idle, wind is light, and the faa-null approach is made directly into the wind. The faa-null approach path has no obstacles, and the landing surface is faa-rm and of ample length to bring the aircraft gradually to a stop. This includes normal runways used for WSC that are asphalt, concrete, solid dirt, gravel or short grass. The selected landing point should be beyond the runway's approach threshold but within the faa-h-8083 1/3 portion of the runway. The factors involved in the procedures described for the normal approach and landing also have applications to the other than normal approaches and landings which are discussed later in this chapter. Therefore, the principles of simple, or normal, operations are explained faa-h-8083 and must be understood before proceeding to more complex operations. To assist the pilot in understanding the factors that influence judgment and procedures, the last part of the approach pattern and the actual landing is divided into 5A phases. Base leg, final approach, roundout, touchdown. After landing roll, remember that the manufacturer's recommended procedures, including aircraft configuration, airspeeds, power, and other information relevant to approaches and landings in a specific make and model aircraft are contained in the Aircraft Flight Manual, AFM, and/or Pilot's Operating Handbook, POH, for that aircraft. If any of the information in this chapter differs from the aircraft manufacturer's recommendations as contained in the AFM/PO, the aircraft manufacturer's recommendations take precedence. Throttle use is discussed in Chapter 2, Aerodynamics. The WSC aircraft has a good glide ratio, and normal landings can easily be done with the power at idle. It is a good practice to master the landings with the throttle at idle so that the glide angle, speeds, and descent rates become habit and part of a normal routine. This is helpful so that, if there is an engine failure, the pilot is accustomed to landing with minimum power and is able to spot land the WSC aircraft for emergency conditions at or beyond a specified point. As a general practice for normal landings in calm conditions or a slight headwind, the throttle should be brought back to idle at the start of the base leg for landings. Title 14 of the Code of Federal Regulations, 14 CFR, Section 91.119, Minimum Safe Altitudes, General, is an important safety precaution and states, except when necessary for takeoff or landing, no person may operate an aircraft anywhere below an altitude allowing, if a power unit fails, an emergency landing without undue hazard to persons or property on the surface. This allows long final approaches with power when necessary, but overall, it is important to be no lower than an altitude from which you can glide to a safe landing area. For the purposes of this approach and landing discussion, it is assumed that there are no safe landing areas other than the runway. It should be noted that the power is above idle for some landing situations such as students faa-h-8083 learning to land. A slower rate of descent is the result of higher power settings. In this case, the landings would be done with a target farther down the runway so a safe landing could always be made with engine failure. Shallower descent angle if directed by air traffic control, ATC, or a longer faa-null approach is required. High winds and or turbulent conditions requiring a higher energy level. For landings where throttle is required, the foot throttle is typically used so the hands can stay on the control bar while approaching the ground for this critical phase of flight. However, the hand/cruise throttle may be set above idle for specific situations as required by the pilot. Higher power settings for approaches and landings are discussed later in this chapter. Base leg. The placement of the base leg is one of the more important judgments made by the pilot in any landing approach. Figure 11.1, the pilot must accurately judge the altitude and distance from which the descent results in landing at the desired point. The base leg should be started at a point where the power can be brought back to idle and the WSC aircraft can glide to the landing spot at the approach speed recommended by the manufacturer. The intended landing point should not be at the end of the runway on a threshold or numbers, but beyond at the landing lines. Figure 11.2, this provides some margin if the landing is shorter than anticipated. For smaller runways that do not have these markings, establish an appropriate landing point beyond the start of the runway, allowing plenty of room for the after-landing roll. At much larger airports, the landing can be done farther down the runway or at a location where the pilot can taxi off the runway and not delay other air traffic behind the aircraft. After turning onto the base leg, the pilot should continue the descent with reduced power and approach airspeed as recommended by the manufacturer. As discussed in Chapter 7, Takeoff and Departure, this speed is at least 1.3 times the stall speed. Landing trims should be adjusted according to manufacturer specifications, if equipped. Drift correction should be established and maintained to follow a ground track perpendicular to the extension of the centerline of the runway on which the landing is to be made. Since the faa-h approach and landing are normally made into the wind, there may be a crosswind during the base leg. The aircraft must be angled sufficiently into the wind to prevent drifting farther away from the intended landing point. The base leg should be continued to the point where a medium to shallow bank turn aligns the aircraft's path directly with the centerline of the landing runway. This descending turn should be completed at a safe altitude that is dependent upon the height of the terrain and any obstructions along the ground track. The turn to the faa-h approach should also be sufficiently above the airport elevation to permit a faa-h approach long enough for the pilot to accurately estimate the resultant point of touchdown, while maintaining the proper approach airspeed. This requires careful planning for the starting point and radius of the turn. Figure 11.3 Normally, it is recommended that the angle of bank not exceed a medium bank because the steeper the angle of bank, the higher the airspeed at which the aircraft stalls. Since the base to faa-h turn is made at a relatively low altitude, it is important that a stall not occur at this point. If an extremely steep bank is needed to prevent overshooting the proper faa-h approach path, it is advisable to discontinue the approach, go around, and plan to start the turn earlier on the next approach rather than risk a hazardous situation. Final approach. After the base to final approach turn is completed, the aircraft should be aligned directly in the extension of the center line of the runway. The objective of a good faa-h approach is to approach the runway with sufficient energy, manufacturer's recommended airspeed, to land at or beyond some predetermined point. The landing area should provide sufficient runway behind for variations in approach conditions and runway ahead to allow either a full stop or a go-around if needed. If there is a crosswind of any kind, the aircraft should be pointed into the wind slightly. See the Crosswind Approaches and Landings section. Focus should be to keep the ground track aligned with the centerline of the runway or landing surface, so that drift, if any, is recognized immediately. On a normal approach, with no crosswind drift, the longitudinal axis should be kept aligned with the runway centerline throughout the approach and landing. After aligning the aircraft with the runway centerline, speed is adjusted as required for the desired rate of descent. Slight increases in power, if lower than expected, may be necessary to maintain the descent angle at the desired approach airspeed. The descent angle should be controlled throughout the approach so that the aircraft lands in the center of the runway at the aiming point, as discussed earlier. The descent angle is affected by all four fundamental forces that act on an aircraft: lift, drag, thrust, and weight. If all the forces are constant, the descent angle is constant in calm air. The pilot can control these forces by adjusting the airspeed and power. The faa-h approach sequence is shown in figures 11-4 through 11-8. In a descent for faa-h approach, if the WSC is slowed with an angle of attack that is too high and without an increase of power, the aircraft settles very rapidly and touches down short of the desired area. For this reason, the pilot should never try to stretch a glide by applying forward control bar pressure alone to reach the desired landing area. Because this brings the speed below the minimum drag speed, the gliding distance decreases if power is not added simultaneously. Additionally, this is a lower energy approach and may be slower than the manufacturer's safe approach speed. The proper angle of descent to the runway must be maintained at the minimum speed recommended by the manufacturer, with a FL adder descent angle obtained with increases in power as required. Steeper descent angles are obtained with headwinds or the pilot increasing speed/decreasing the angle of attack, both of which are covered later in this chapter. Estimating height and movement during the faa-h approach, roundout, and touchdown vision is of prime importance. To provide a wide scope of vision and to foster good judgment of height and movement, the pilot's head should assume a natural, straight-ahead position. The pilot's visual focus should not be crossed on any one side or any one spot ahead of the aircraft. The pilot should maintain a deliberate awareness of the runway centerline, if available, or distance from either side of the runway within his or her peripheral field of vision. Accurate estimation of distances, besides being a matter of practice, dependent upon how clearly objects are seen, Vision must be focused properly so that important objects stand out as clearly as possible. Speed blurs objects at close range. For example, one can note this effect in an automobile moving at high speed. Nearby objects seem to merge together in a blur, while objects farther away stand out clearly. The driver subconsciously focuses the eyes sufficiently far ahead of the automobile to see objects distinctly. The distance at which the pilot's vision is focused should be proportionate to the speed at which the aircraft is traveling over the ground. Thus, as speed is reduced during the roundout, the focus distance ahead of the aircraft should be decreased accordingly. If the pilot attempts to focus on a reference that is too close or looks directly down, the reference is blurred, and the reaction is either too abrupt or too late. In this case, the pilot's tendency is to overcontrol, round out high, and make a stalled, drop-in landing. When the pilot focuses too far ahead, accuracy in judging the closeness of the ground is lost and the consequent reaction is too slow since there is no apparent necessity for action. This results in the aircraft flying into the ground nose faa-h-8083 without a proper roundout. The best way to recognize and become accustomed to heights and speeds for a particular WSC aircraft is to perform low passes over the runway, as discussed earlier, with energy management. Perform a normal approach faa-h-8083, then a high energy pass at a higher speed, and then medium energy passes at lower speeds. These exercises are performed faa-h-8083 in calm winds at a height, as an example, at which the wheels are 10 feet above the runway, then lowering to just inches above the runway as the pilot's skills build. The objective is to become proficient at flying straight down the runway centerline at a constant altitude. This exercise provides the opportunity to determine height and speed over the runway before any landings are performed. These should generally be performed in mild conditions. Higher energy and greater heights above the runway are required in windier and bumpier conditions. Roundout flare. The roundout is a slow, smooth transition from a normal approach speed to a landing attitude, gradually rounding out the flight path to one that is parallel with, and within a very few inches above, the runway. When the aircraft, in a normal descent, approaches within what appears to be 10 to 15 feet above the ground, the roundout or FLR should be started and be a continuous process slowing until the aircraft touches down on the ground. It should be noted that the terms roundout and FLR are defined and used interchangeably throughout the aviation industry for slowing the aircraft during final approach and touching down. The term roundout is used in this handbook since it provides a better description for the WSC landing process, and WSC students are more successful learning landings using the term roundout instead of FLR. As the aircraft reaches a height where the back wheels are 1 to 2 inches above the ground, the roundout is continued by gradually pushing the control bar forward as required to maintain 1 to 2 inches above the runway as the WSC aircraft slows. Figure 11.9, this causes the aircraft's nose wheel to gradually rise to the desired landing attitude. The OA should be increased at a rate that allows the aircraft to continue flying just above the runway as forward speed decreases until the control bar is full forward and the back wheels settle onto the runway. During the roundout, the airspeed is decreased to touchdown speed while the lift is controlled so the aircraft settles gently onto the landing surface. The roundout should be executed at a rate at which the proper landing attitude and the proper touchdown airspeed are attained simultaneously just as the wheels contact the landing surface. The rate at which the roundout is executed depends on the aircraft's height above the ground, the rate of descent, and the airspeed. A roundout started excessively high must be executed more slowly than one from a lower height to allow the aircraft to descend to the ground while the proper landing attitude is being established. The rate of rounding out must also be proportionate to the rate of closure with the ground. When the aircraft appears to be descending very slowly, the increase in pitch attitude, slowing of the WSC, must be made at a correspondingly low rate. Visual cues are important in roundout at the proper altitude and maintaining the wheels a few inches above the runway until eventual touchdown. Roundout cues are dependent primarily on the angle at which the pilot's central vision intersects the ground, or runway, ahead and slightly to the side. Proper depth perception is a factor in a successful roundout, but the visual cues used most are those related to changes in runway or terrain perspective and to changes in the size of familiar objects near the landing area such as fences, bushes, trees, hangars, and even sod or runway texture. The pilot should direct central vision at a shallow downward angle of 10 degrees to 15 degrees toward the runway as the roundout is initiated. Figure 11.10, maintaining the same viewing angle causes the point of visual interception with the runway to move progressively rearward toward the pilot as the aircraft loses altitude. This is an important visual cue in assessing the rate of altitude loss. Conversely, forward movement of the visual interception point indicates an increase in altitude and would mean that the pitch angle was increased too rapidly, resulting in an over-roundout. The following are also used to judge when the wheels are just a few inches above the runway: location of the visual interception point in conjunction with assessment of FLA velocity of nearby off-runway terrain, and the similarity in appearance of height above the runway ahead of the aircraft to the way it looked when the aircraft was taxied prior to takeoff. A common error during the roundout is rounding out too much and too fast. This error can easily be avoided by gradually increasing the OO with a controlled descent until the wheels are 1 inch above the surface, and never climbing during a roundout with a gradual and controlled roundout. Touchdown. After a controlled roundout, the touchdown is the gentle settling of the aircraft onto the landing surface. For calm air conditions, the roundout can be made with the engine idling, and touchdown can be made at minimum controllable airspeed so that the aircraft touches down on the main gear at the approximate stalling speed. As the aircraft settles, the proper landing attitude is attained by application of whatever control bar forward pressure is necessary. In calm wind conditions, the goal is to round out smoothly and have the control bar touch the front tube as the back wheels touch the ground. Figures 11 to 11 through 11 to 14. Once the rear wheel settles to the surface, the nose wheel settles to the ground. The control bar should be pulled all the way back to eliminate the possibility of lifting off the ground because of a wind gust. Pulling the nose down completely can also be used for aerodynamic braking if needed. After landing roll, the landing process must never be considered complete until the aircraft decelerates to normal taxi speed during the landing roll or has been brought to a complete stop when clear of the landing area. Many accidents have occurred as a result of pilots abandoning their vigilance and positive control after getting the aircraft on the ground. The pilot must make only slight turns to maintain direction until the WSC has slowed to taxiing speed. An abrupt turn at high speed could possibly lift a rear wheel, roll the WSC over, or force the wingtip to the ground. The WSC must slow to taxiing speed before any sharp turn can be made to exit the runway. The brakes of an aircraft serve the same primary purpose as the brakes of an automobile, to reduce speed on the ground. Maximum brake effectiveness is just short of the skid point. If the brakes are applied so hard that skidding takes place, braking becomes ineffective. Skidding can be stopped by releasing the brake pressure. Also, braking effectiveness is not enhanced by alternately applying and reapplying brake pressure. The brakes should be applied firmly and smoothly as necessary. WSC aircraft have nose wheel or rear wheel braking systems. For nose wheel systems, if braking is required right away, the nose should be lowered so the nose wheel touches the ground and the brakes can be applied. The nose should be lowered for any aerodynamic braking at the higher speeds. Lowering the nose also provides greater force on the front wheel for superior braking effectiveness. Any skidding of the front wheel with braking causes the loss of directional control of the WSC aircraft, and the skidding must be stopped by letting up on the brake. Skidding can be the greatest problem operating on slick surfaces such as wet grass. Rear wheel braking systems are heavier and more complex, but provide better braking force because there are 2 wheels instead of 1 and there is more weight on the rear wheels. Braking effectiveness should be evaluated by the pilot for each type of runway being used. If the available runway permits, the speed of the aircraft should be allowed to dissipate in a normal manner with minimum use of brakes. Figure 11.15, the control bar serves the same purpose on the ground as in the air. It changes the lift and drag components of the wings. During the after-landing roll, the control bar should be used to keep the wings level in much the same way it is used in ight. If a wing starts to rise, roll control should be applied to lower it. Procedures for crosswind conditions are explained further in the Crosswind Approach and Landings section of this chapter. Effective headwinds. During final approach, a headwind plays a prominent role in the gliding distance over the ground. Strong headwinds decrease the glide as shown in the comparison in Figure 11.16a with no wind normal glide versus Figure 11.16b in headwind with steeper glide. To account for a steeper glide in a headwind, the base leg must be positioned closer to the approach end of the runway than would be required with a light wind. Therefore, the base leg must be made closer to the runway to land in the intended area in a headwind. Figure 11.16c. However, if more headwind is experienced during final approach, increased power is required to make the intended landing area. Figure 11.16d. Naturally, the pilot does not have control over the wind but may correct for its effect on the aircraft's descent by adjusting the base leg of the pattern. The wind can vary significantly at different attitudes and locations in the pattern. If the pilot does not notice the headwind until the base leg, the base leg should be cut short and the pilot should head towards the runway sooner. This would provide the best possibility of making the runway if there is an engine failure in this situation. Figure 1117, additionally, during strong headwinds, more energy, power and airspeed should be used since the wind gradient, slowing of the wind near the ground because of the friction of the ground, could reduce the airspeed and cause a stall on approach near the ground in higher winds. Stabilized approach. Concept of stabilized approach is one in which the pilot establishes and maintains a constant angle glide path toward a predetermined point on the landing runway. It is based on the pilot's judgment of certain visual clues and depends on the maintenance of a constant final descent airspeed. An aircraft descending on final approach at a constant rate and airspeed is traveling in a straight line toward a point on the ground ahead. This point is not the point on which the aircraft touches down because some faa-h inevitably occurs during the roundout. The point toward which the aircraft is progressing is termed the aiming point. Figure 1118, it is the point on the ground at which, if the aircraft maintains a constant glide path and was not rounded out for landing, it would strike the ground. To a pilot moving straight ahead toward an object, it appears to be stationary. This is how the aiming point can be distinguished, it does not move. However, objects in front of and beyond the aiming point do appear to move as the distance is closed, and they appear to move in opposite directions. During instruction and landings, one of the most important skills a student pilot must acquire is the use of visual cues to accurately determine the true aiming point from any distance out on final approach. From this, the pilot is able not only to determine if the glide path results in an undershoot or overshoot, but also to predict the touchdown point to within a few feet, taking into account faa-h during roundout. For a constant angle glide path, the distance between the horizon and the aiming point remain constant. If a final approach descent has been established but the distance between the perceived aiming point and the horizon appears to increase, aiming point moving down, away from the horizon, then the true aiming point and subsequent touchdown point is farther down the runway. If the distance between the perceived aiming point and the horizon decreases, aiming point moving up toward the horizon, the true aiming point is closer than perceived. When the aircraft is established on final approach, the shape of the runway image also presents clues regarding what must be done to maintain a stabilized approach to a safe landing. A runway is normally shaped in the form of an elongated rectangle. When viewed from the air during the approach, perspective causes the runway to assume the shape of a trapezoid with the far end appearing narrower than the approach end, and the edge lines converging in the distance. If the aircraft continues down the glide path at a constant angle, stabilized, the image the pilot sees is still trapezoidal but of proportionally larger dimensions. During a stabilized approach, the runway shape does not change. Figure 1119, if the approach becomes shallower, the runway appears to shorten and become wider. Conversely, if the approach is steepened, the runway appears to become longer and narrower. Figure 1120, the objective of a stabilized approach is to select an appropriate touchdown point on the runway and adjust the glide path so that the true aiming point and the desired touchdown point coincide. Immediately after rolling out of base leg and onto final approach, the pilot should adjust the speed so that the aircraft descends directly toward the aiming point. With the approach set up in this manner, the pilot is free to devote full attention to outside references. The pilot should not stare at any one place, but rather scan from one area to another, such as from the aiming point to the horizon, to the trees and bushes along the runway, to an area well short of the runway, and back to the aiming point. In this way, the pilot is more apt to perceive a deviation from the desired glide path and whether or not the aircraft is proceeding directly toward the aiming point. If the pilot perceives any indication that the aiming point on the runway is not where desired, an adjustment must be made to the glide path. This in turn moves the aiming point. For instance, if the pilot perceives that the aiming point is significantly short of the desired touchdown point and results in an undershoot, an increase in power is warranted. The minimum airspeed recommended by the manufacturer must be maintained. This results in a shallowing of the glide path with the resultant aiming point moving toward the desired touchdown point. Conversely, if the pilot perceives that the aiming point is farther down the runway than the desired touchdown point and results in an overshoot, the glide path should be steepened by an increase in speed with the throttle at idle. It is essential that deviations from the desired glide path be detected early, so that only slight and infrequent adjustments to glide path are required. If a situation arises in which the required corrections become larger, and possibly more frequent, as the aircraft draws closer to the runway, an unstabilized approach results. Common errors in the performance of normal approaches and landings include the following: not realizing there is a tailwind during downwind to complete an early base, inadequate wind drift correction on the base leg. Overshooting or undershooting the turn onto final approach, unstabilized approach, attempting to maintain altitude or reach the runway by slowing WSC aircraft below the minimum manufacturer's recommended approach airspeed, gaining any altitude during the roundout, rounding out too fast during landing, focusing too close to the aircraft, resulting in an overly high roundout, focusing too far from the aircraft, resulting in an overly low roundout, touching down prior to attaining proper landing attitude, failure to lower the nose after the rear wheels touch down, failure to lower the nose after the front wheel touches down, excessive braking after touchdown go-around, rejected landings. Whenever landing conditions are not satisfactory, a go-around is warranted. There are many factors that can contribute to unsatisfactory landing conditions. Situations such as ATC requirements, unexpected appearance of hazards on the runway, overtaking another aircraft, wind shear, wake turbulence, mechanical failure and/or an unstabilized approach are all examples of reasons to discontinue a landing approach and make another approach under more favorable conditions. The assumption that an aborted landing is invariably the consequence of a poor approach, which in turn is due to insufficient experience or skill, is a fallacy. The go-around is not strictly an emergency procedure. It is a normal maneuver that may at times be used in an emergency situation. Like any other normal maneuver, the go-around must be practiced and perfected. The ight instructor should emphasize early in the student pilot's training that the go-around maneuver is an alternative to any approach and/or landing. Although the need to discontinue a landing may arise at any point in the landing process, the most critical go-around is one started when very close to the ground. Therefore, the earlier a condition that warrants a go-around is recognized, the safer the go-around/rejected landing is. The go-around maneuver is not inherently dangerous in itself. It becomes dangerous only when delayed unduly or executed improperly. Delay in initiating the go-around normally stems from one or both of two sources. 1. Landing expectancy or set, the anticipatory belief that conditions are not as threatening as they are and that the approach will surely be terminated with a safe landing. 2. Pride, the mistaken belief that the act of going around is an admission of failure to execute the approach properly. The improper execution of the go-around maneuver stems from a lack of familiarity with the two cardinal principles of the procedure, power and speed. Power is the pilot's faa-h-8083-5 concern. The instant the pilot decides to go around, full or maximum allowable takeoff power must be applied smoothly and without hesitation and held until faa-h-8083 speed and controllability are restored. Applying only partial power in a go-around is never appropriate unless the WSC aircraft is at an unusually high pitch angle. The pilot must be aware of the degree of inertia that must be overcome before an aircraft that is settling toward the ground can regain sufficient airspeed to become fully controllable and capable of turning safely or climbing. The application of power should be smooth as well as positive. Abrupt movements of the throttle in some aircrafts causes the engine to falter. Speed is always critical when close to the ground. When power is added, a deliberate effort on the part of the pilot is required to keep the nose from pitching up prematurely. The aircraft executing a go-around must be maintained well beyond the stall point before any effort is made to gain altitude or to execute a turn. Raising the nose too early may produce a stall from which the aircraft could not recover if the go-around is performed at a low altitude. The manufacturer's recommended climb speed should be established and maintained during the initial phase of the go-around. A concern for quickly regaining altitude during a go-around produces a natural tendency to push the nose up. The pilot executing a go-around must accept the fact that an aircraft will not climb until it can FLY, and it will not FLY below stall speed. In some circumstances, it may be desirable to lower the nose briefly to gain airspeed. Figure 1121, during the initial part of an extremely low go-around, the aircraft may settle onto the runway and bounce. This situation is not particularly dangerous if the aircraft is kept straight and a constant, safe speed is maintained. The aircraft is rapidly approaching safe faa-h-8083 speed and the advanced power will cushion any secondary touchdown. Common errors in the performance of go-around, rejected landings, are: failure to recognize a condition that warrants a rejected landing, indecision, delay in initiating a go-around, failure to apply maximum allowable power in a timely manner, improper speed, attempting to climb out of ground effect prematurely, and failure to adequately compensate for torque/P factor. Short and soft field landing techniques. Many WSC aircraft land routinely on short and soft faa-h-8083s. The type of WSC and appropriate systems for short and soft faa-h-8083 was discussed in the Components and Systems chapter. Here, some techniques for these landing areas are discussed. Short field approaches and landings. Short field approaches and landings require the use of procedures for approaches and landings at fields with a relatively short landing area or where an approach is made over obstacles that limit the available landing area. Figure 1122, as in short faa-h-8083 takeoffs, It is one of the most critical of the maximum performance operations. It requires that the pilot fly the aircraft at one of its crucial performance capabilities while close to the ground in order to land safely within confine-net areas. To land within a short faa-h or confine-net area, the pilot must have precise, positive control of the rate of descent and airspeed to produce an approach that clears any obstacles, results in little or no FL loading during the roundout, and permits the aircraft to be stopped in the shortest possible distance. As with the short takeoff maneuver, this should only be done for unusual situations or emergency operations and is not recommended. There are numerous airports, faa-hs, and other areas to land, so pre-flight planning should avoid short faa-h landings. However, short faa-h procedures are provided for information. A stabilized approach is essential. These procedures generally involve the starting to final approach from an altitude of at least 500 feet higher than the touchdown area. In the absence of a manufacturer's recommended approach speed and in calm winds, example approach speeds are 1.3 times the stall speed or 8 knots above the stall speed. For example, in an aircraft that stalls at 30 knots with power off, the approach speed should be 38 to 40 knots. This maneuver should not be performed in gusty air because of the slow speeds and close proximity to the ground. If it is necessary to accomplish in gusty air, no more than 1/2 the gust factor should be added. An excessive amount of airspeed could result in a touchdown with an after-landing roll that exceeds the available landing area. For the steepest glide angle to clear obstacles such as trees or buildings, the maneuver should be performed at idle power. If the landing surface does not have obstacles that must be flown over, power on approach may be used to reach the landing surface. The pilot should simultaneously adjust the power and the speed to establish and maintain the proper descent angle. A coordinated combination of both speed and power, if used, adjustments is required to set up a stabilized approach. The short faa-h approach and landing is in reality an accuracy approach to a spot landing. The procedures previously outlined in the section on the stabilized approach concept should be used. If it appears that the obstacle clearance is excessive and touchdown will occur well beyond the desired spot, leaving insufficient room to stop, lowering the pitch attitude and reducing power, if used, steepen the descent path and increase the rate of descent. If it appears that the descent angle will not ensure safe clearance of obstacles, power should be increased to shallow the descent path and decrease the rate of descent. Care must be taken to avoid an excessively low airspeed. If the speed is allowed to become too low, an increase in pitch and application of full power may result in a further rate of descent. This occurs when the OA is too great and creating so much drag that the maximum available power is insufficient to overcome it. This is generally referred to as operating in the region of reversed command or operating on the backside of the power curve. Because the final approach over obstacles is made at a relatively steep approach angle and at the minimum manufacturer's recommended approach speed, the initiation of the roundout must be judged accurately to avoid flying into the ground or stalling prematurely and sinking rapidly. A lack of FL loading during the roundout with sufficient control to touch down properly is one verification that the approach speed was correct. Upon touchdown, the nose should be brought down completely for aerodynamic braking and providing maximum pressure on the wheels for using the braking system. Immediately upon touchdown, appropriate braking should be applied to minimize the after-landing roll. The aircraft should be stopped within the shortest possible distance consistent with safety and controllability. If the situation arises and the minimum landing distance is required, the WSC can be landed above the normal speed, the nose brought down for aerodynamic braking while the brakes are applied for the shortest distance possible. Soft and rough field approaches and landings. Landing on faa-hs that are rough or have soft surfaces, such as snow, sand, mud, tall grass, or a rocky/bumpy faa-h requires unique procedures. When landing on such surfaces, the objective is to touch down as smoothly as possible and at the lowest possible landing speed. The pilot must control the aircraft so that the wings support the weight of the aircraft as long as is practical to minimize drag and stresses imposed on the landing gear by the rough or soft surface. Similar to the soft faa-h for takeoff, proper gear, specifically big tires with a large wing and overall low weight, should be utilized for soft or rough faa-h operations. Refer to appropriate gear and warnings in Chapter 7, Takeoff and Departure Climbs, for soft or rough faa-h operation as a prerequisite for this chapter. The approach for the soft faa-h landing is similar to the normal approach used for operating into long, FIRM landing areas. The major difference between the two is that, during the soft or rough faa-h landing, the distance on the soft/rough faa-h is minimized and the weight is kept off the wheels by the lift of the wing when on the soft/rough faa-h. Power can be used throughout the level off and touchdown to ensure touchdown at the lowest possible airspeed, with the WSC aircraft FL'd onto the ground with the weight fully supported by the wings. The touchdown should be planned for minimal taxi distance to the stopping point, so there is the shortest possible distance with weight on the landing gear on the rough/soft surface. Figure 1123. Touchdown on a soft or rough faa-h should be made at the lowest possible airspeed with the aircraft in a nose-high pitch attitude. After the main wheels touch the surface, the pilot should hold bar forward pressure to keep the nose wheel off the surface. Using forward control bar pressure and engine power, the pilot can control the rate at which the weight of the aircraft is transferred from the wings to the wheels. Field conditions may warrant that the pilot maintain a ight condition where the main wheels are just touching the surface, but the weight of the aircraft is still being supported by the wings until a suitable taxi surface is reached. At any time during this transition phase, before the weight of the aircraft is being supported by the wheels and before the nose wheel is on the surface, the pilot should be able to apply full power and perform a safe takeoff, obstacle clearance and faa-h length permitting, should the pilot elect to abandon the landing. Once committed to a landing, the pilot should gently lower the nose wheel to the surface. A slight reduction of power usually helps ease the nose wheel down. The use of brakes on a soft faa-h is not needed and should be avoided, as this tends to impose a heavy load on the nose gear due to premature or hard contact with the landing surface, causing the nose wheel to dig in. The soft or rough surface itself provides sufficient reduction in the aircraft's forward speed. Often upon landing on a very soft faa-h, the pilot needs to increase power to keep the aircraft moving and from becoming stuck on the soft surface. Power on approach and landing. For turbulent air, power on approaches at an airspeed above the normal approach speed should be used for landing in turbulent air. This provides for more energy and positive control of the aircraft when strong horizontal wind gusts, wind shear, or up and down drafts are experienced. Like other power on approaches, when the pilot can vary the amount of power, a coordinated combination of both speed and power adjustments is usually required. It is easiest to think of FLYing the aircraft onto the ground at an airspeed above the stall speed. The additional power provides the pilot the ability to reduce the descent rate to touch the wheels gently to the surface at a higher speed. Landing in turbulent air is where practice and experience in energy management are utilized. This precise coordination of power and speed for higher energy landings should faa-h be practiced in calm air and can be used as the next step in learning landings after the student becomes proficient at low approaches. To determine the additional approach speed to FLYing in turbulence, one procedure is to use the normal approach speed plus 1/2 of the wind gust factors. The wind gust factor is determined by how much the airspeed varies while FLYing. If the normal approach speed is 50 knots and the wind gusts are at 15 knots, an airspeed of 57 knots is appropriate. Another method is to ensure the aircraft is at least at VY speed plus the wind gust factor. In any case, the airspeed that the aircraft manufacturer recommends. An adequate amount of power should be used to maintain the proper airspeed and descent path throughout the approach, and the throttle retarded to idling position only after the main wheels contact the landing surface. Care must be exercised in not closing the throttle before the pilot is ready for touchdown. In this situation, the sudden or premature closing of the throttle may cause a sudden increase in the descent rate that could result in a hard landing. Landings from power on approaches in turbulence should be such that the touchdown is made with the aircraft in approximately level FLYed attitude. The pitch attitude at touchdown should be only enough to prevent the nose wheel from contacting the surface before the main wheels have touched the surface. Most WSC are designed so the front wheel is higher than the back wheels in this situation, but each WSC is different. This must be evaluated for each model. After touchdown, the pilot should reduce the throttle to idle and pull the control bar all the way to the chest to lower the nose and prevent the WSC aircraft from lifting off until it slows below the stall speed. The aircraft should be allowed to decelerate normally with the aerodynamic braking of the wing with the nose lowered, and assisted by the wheel brakes as required. Crosswind approaches and landings. Many runways or landing areas are made such that landings must be made while the wind is blowing across rather than parallel to the landing direction. All pilots should be prepared to cope with these situations when they arise. The same basic principles and factors involved in a normal and power on approach and landing apply to a crosswind approach and landing, therefore, only the additional procedures required for correcting for wind drift are discussed here. Crosswind approaches and landings are more challenging than normal landings because of the wind drift in the pattern, crab angles on approach, and generally more mechanical turbulence for the final approach and roundout because of buildings and/or trees along the sides of the runway. Since mechanical turbulence would typically increase as the aircraft descends closer to the ground, power on approaches and techniques for FLYing in turbulence should be utilized. Crosswind pattern procedures. Since WSC aircraft typically fly tighter patterns, the pattern should be modified if the crosswind is in a direction pushing the WSC aircraft toward the runway. Refer to Figure 1124 for the following discussion. The normal or typical pattern downwind and base for calm winds is shown in blue. This pattern would also be used if there were an opposite crosswind from that shown blowing from the runway toward the base leg. If a strong crosswind, 15 knots as an example, which is a limitation for many WSC, is noticed while flying, the downwind or the runway wind indicators show this crosswind, at A the decision should be made to modify the pattern, making it wider by flying out to location B. An extended downwind should then be made farther than the typical normal pattern to C. This provides additional distance from the runway for the base leg, which will be at a much higher ground speed than normal because the WSC is flying in a strong tailwind from point C to D. The turn must be made at D to set up for faa-h approach at E, where there is a signify can't crab angle. From the faa-h approach at E to touchdown, the pilot has sufficient time to establish the ground track in the center of the runway and evaluate if the landing should be completed, a go-around performed, or a different landing location selected with more favorable wind conditions. Effects and hazards of high crosswinds for approaches and landings. Figure 1124 illustrates a scenario that includes the effects and hazards of high wind, referencing ground speed, high rates of turn, and power requirements for making downwind turns in close proximity to the ground. During the downwind leg of the pattern, the pilot does not notice the strong wind blowing the WSC aircraft into the runway. From points A to W, the pilot reduces power as normal but does not crab into the wind and drifts with the wind toward the runway between points A and W. This leads the pilot to be closer to the runway when he or she turns onto base. The pilot turns onto base and is traveling at high ground speed, and the strong tailwind leads to the pilot passing the runway centerline normal faa-h approach at point X. From points X to Y, the pilot starts the turn for faa-h approach late because of the high ground speed. The WSC aircraft past the runway centerline leads the pilot to increase the bank to make it back to the centerline. The previous errors lead the pilot into a high bank angle at low altitude pointed down in a rapid descent. This leads the pilot to apply full power at Y, which drives the WSC aircraft into ground at point Z. The error chain that led to this accident could have been avoided at two primary points. First, the pilot should have noticed flying in a crosswind or indications of a strong crosswind on the runway from airport wind indicators at A. He or she should have then widened the pattern into the crosswind from A to B and performed the recommended crosswind procedure described earlier. Second, if the pilot did not realize the high wind blowing to the runway until point X was reached, the wings should have been leveled and a go-around performed without trying to make it back to the runway as shown in the yellow go-around paths shown on Figure 1124. For strong crosswinds beyond the capabilities of the pilot or limitations of the WSC aircraft, an alternate landing strip should be found. This could be another airport or landing strip that faces into the wind. An option at uncontrolled airports is to choose an alternate runway or even a taxiway that faces into the wind. Some of the larger airports with wide runways make it possible to land at an angle if needed, some are wide enough to land across the main runway. At towered airports, the air traffic controller can assist the pilot and provide an alternate landing area if requested. Crosswind landings. When in faa-h approach, the wind correction angle, crab angle, is established by heading toward the wind with the wings level so that the aircraft's ground track remains aligned with the center line of the runway. Figure 1125, this crab angle is maintained all the way to touchdown, when the rear wheels hit faa-h and rotate the carriage and wing around so the front wheel touches the ground with the carriage going straight. However, if in turbulent air or pitched forward during the touchdown, with the front wheel touching the ground faa-h, the pilot should lightly control the steering of the front wheel to be headed in the direction the carriage is going. WSC carriage front landing gear typically has camber that tends to steer the front wheel naturally in the direction of travel, so a light touch on the front wheel as it touches the ground allows it to find its own direction of travel. Once the front wheel is on the ground, lower the nose to keep the WSC on the ground and steer as required down the center of the runway. The procedure for the wing during the roundout is the same as that for normal and turbulent roundout and touchdowns. The exception is that after touchdown the windward wings should be lowered slightly so the wind cannot get under it to flip the WSC aircraft during later landing, roll and taxi. Maximum crosswind velocities. Takeoffs and landings in certain crosswind conditions are inadvisable and even dangerous. Figure 1126, if the crosswind is great enough, a hazardous landing condition may result. Therefore, takeoff and landing capabilities with respect to the reported surface wind conditions and available landing directions must be considered. WSC crosswind limitations have been tested and are included in the PO. The headwind and crosswind components for a given situation can be determined by reference to a crosswind component chart. Figure 1127. It is imperative that pilots determine the maximum crosswind component of each aircraft FL and avoid operations in wind conditions that exceed the capability of the aircraft. The Automatic Weather Observation System, AWOS, or Automatic Surface Observation System, ASOS, at airports is useful in determining the measured velocity for this evaluation. Common errors in the performance of crosswind approaches and landings include failure to recognize a strong crosswind blowing at the runway during the downwind leg, failure to modify the pattern for strong crosswind conditions, failure to do a go-around when the final approach to the runway is downwind of the runway centerline, attempting to land in crosswinds that exceed the pilot's capabilities, attempting to land in crosswinds that exceed the aircraft's maximum demonstrated crosswind component, inadequate compensation for wind drift on the turn from base leg to final approach, resulting in undershooting or overshooting, inadequate compensation for wind drift on final approach, unstabilized approach, touchdown while drifting, excessive pressure on the nose wheel steering during touchdown, excessive airspeed on touchdown, failure to apply appropriate FL-ight control inputs during rollout, failure to maintain direction control on rollout, and excessive braking. Steep approaches. A steep approach is a valuable maneuver for WSC aircraft. Figure 1128. It is better to be too high for an approach rather than too low for an approach in case the engine fails. A steep approach can be used to reach the landing point easily. If too low, the aircraft lands short. Steep approaches are used routinely by many pilots to help ensure making the landing point if the engine fails. The two types of procedures, or a combination thereof, used are based on the angle of descent required. To perform a steep approach, evaluation of the situation considers the angle of descent required to land at or within 400 feet of a specified at point in which the steep angle or alternating turns are utilized. For all steep approaches, the throttle is brought to idle. Steep angle. For situations in which an increase in the descent angle is needed for the intended landing spot, the normal procedure is to increase speed above the best LD speed in order to descend. The greater the speed is, the greater the parasitic drag and descent angle. Each design has different descent rates based on the parasitic drag of the wing and carriage. For example, a single surface with an exposed crossbar wing and a stick carriage, no streamlined cowling, increases the descent angle quickly because of the dramatic increases in drag with increased speed. A double surface wing with a streamlined carriage does not develop parasitic drag as fast with increased speed and is less able to achieve a steep angle with increased speed. The pilot should understand that this characteristic is unique to the make/model being FL-own. This steep angle technique is the optimum steep approach procedure because the aircraft is lined up on the runway and the pilot can easily judge the glide slope using the stabilized approach method covered earlier. Figure 1129, increase speed as required to obtain the descent angle for the intended touchdown point. Use the stabilized approach technique to obtain the increased angle for the aiming point. At the higher speeds and greater descent, slow to the normal approach speed, intersect the normal final approach path, and perform the landing required for that particular situation, calm air/crosswind/turbulent air. As the student gains proficiency at steep approach techniques, the altitude to transition from the high-speed steep angle to the normal approach speed can be lowered, and eventually combined into one continuous roundout for landing started at a higher altitude than the normal approach and roundout. For this situation, note that with the increased speed the roundout covers additional distance that should be accounted for as the speed is decreased. Alternating turns if at a height at which a steep approach is necessary, but the aircraft is too high to obtain an angle steep enough to make the intended landing area. Alternating turns can be made to decrease altitude to a point at which the steep angle technique could be applied for the remainder of the descent. These alternating turns should be performed no lower than 400 feet above ground level AGL. The turns should be an equal distance from the runway centerline extension to keep track and maintain the relative position on the runway centerline. The bank and direction of turns across the runway centerline should be determined by how much altitude must be lost to position the WSC aircraft for utilization of the steep angle technique for the remainder of the steep approach, if required. Figure 1130, Power-off accuracy approaches. Power-off accuracy approaches are made by gliding with the engine idling through a specific pattern to a touchdown beyond and within 200 feet of a designated line or mark on the runway. The objective is to instill in the pilot the judgment and knowledge of procedures necessary for accurate FL-ight, without power, to a safe landing. This simulates procedures for an emergency engine out situation. The ability to estimate the distance an aircraft glides to a landing is the real basis of all power-off accuracy approaches and landings. This largely determines the amount of maneuvering that may be done from a given altitude. In addition to the ability to estimate distance, the ability to maintain the proper glide while maneuvering the aircraft is required. With experience and practice, altitudes up to approximately 1,000 feet can be estimated with fair accuracy, while above this level the accuracy and judgment of height above the ground decreases since features tend to merge. The best aid in perfecting the ability to judge height above this altitude is altimeter indications and associating them with the general appearance of the Earth. The judgment of altitude in feet, hundreds of feet, or thousands of feet is not as important as the ability to estimate gliding angle and its resultant distance. The pilot who knows the normal glide angle of the aircraft can estimate with reasonable accuracy the approximate spot along a given ground path at which the aircraft lands, regardless of altitude. The pilot who also has the ability to estimate altitude accurately can judge how much maneuvering is possible during the glide, which is important to the choice of landing areas in an actual emergency. Unlike a normal approach in which power is available when needed, for a power-off approach the power is faa crossed at the idle setting. Pitch attitude is adjusted to control the airspeed, which also changes the glide or descent angle. As discussed in the basic flight maneuvers descents and the steep approach maneuver, lowering the nose to a speed above the best glide angle causes the descent angle to steepen. If the airspeed is too high, raise the nose, and when the airspeed is too low, lower the nose. If the pitch attitude is raised too high, the aircraft settles rapidly due to low airspeed and insufficient lift. For this reason, never try to stretch a glide to reach the desired landing spot. Uniform approach patterns such as the 90 degrees, 180 degrees, or 360 degrees power-off approaches are described further in this chapter. Practice in these approaches provides the pilot with a basis on which to develop judgment in gliding distance and in planning an approach. The 180 degrees power-off approach from pattern altitude should be the normal landing procedure in calm winds. This should become routine and develop the ability to accurately judge the landing for an engine-out situation. Remember, the steep approach technique can always be used if the aircraft is a little high, but do not stretch a glide by lowering the speed if too low. The basic procedure in these approaches involves closing the throttle at a given altitude and gliding to a key position. This position, like the pattern itself, must not be allowed to become the primary objective. It is merely a convenient point in the air from which the pilot can judge whether the glide safely terminates at the desired spot. The selected key position should be one that is appropriate for the available altitude and the wind condition. From the key position, the pilot must constantly evaluate the situation. It must be emphasized that, although accurate spot touchdowns are important, safe and properly executed approaches and landings are vital. The pilot must never sacrifice a good approach or landing just to land on the desired spot. All power-off approaches must be practiced to avoid interfering with normal traffic CFLO at busy airports, so the place and timing must be evaluated by the instructor to prevent airport traffic conflicts. This is especially important for the 360 degrees power-off approach. 90 degrees power-off approach. The 90 degrees power-off approach is made from a base leg and requires only a 90 degrees turn onto the faa-h approach. The approach path may be varied by positioning the base leg closer to or farther away from the approach end of the runway according to wind conditions. Figure 1131, the glide from the key position on the base leg through the 90 degrees turn to the faa-h approach is the faa-h part of all accuracy landing maneuvers. Steep approach procedures may be used during the faa-h approach if needed. The 90 degrees power-off approach usually begins from a rectangular pattern below normal pattern altitude as long as this point is above 500 feet AGL. The before landing checklist should be completed on the downwind leg. After a medium bank turn onto the base leg is completed and key position obtained, the throttle should be completely reduced to idle and the airspeed set to approach speed. Figure 1132, at this position, the intended landing spot appears to be on a 45 degrees angle from the aircraft's nose. The pilot can determine the strength and direction of the wind from the amount of crab necessary to hold the desired ground track on the base leg. This helps in planning the turn onto the faa-h approach. The base to faa-h turn should be planned and accomplished so that upon rolling out of the turn the aircraft is aligned with the runway centerline. Slight adjustments in pitch attitude may be necessary to control the glide angle and airspeed. However, never try to stretch the glide to reach the desired landing spot. After the faa-h approach glide has been established, full attention is given to making a good, safe landing rather than concentrating on the selected landing spot. In any event, it is better to execute a good landing 200 feet from the spot than to make a poor landing precisely on the spot. 180 degrees power off approach. The 180 degrees power off approach is executed by gliding with the power off from a given point on a downwind leg to a preselected landing spot. Figure 1133, it is an extension of the principles involved in the 90 degrees power off approach just described. Its objective is to further develop judgment in estimating distances and glide ratios, in that the aircraft is FL-on without power from a higher altitude and through a 90 degrees turn to reach the base leg position at a proper altitude for executing the 90 degrees approach. The 180 degrees power off approach requires more planning and judgment than the 90 degrees power off approach. In the execution of 180 degrees power off approaches, the aircraft is FL-on on a downwind heading parallel to the landing runway. The altitude from which this type of approach should be started in the downwind leg is at a normal pattern altitude. This power-off approach should be the normal procedure except for normal light wind landings. The throttle can be brought back to idle between the downwind leg key position and the turn onto the base leg depending on the height and distance from the runway. When abreast of or opposite the desired landing spot or a location closer to the turn onto base, if the WSC is further from the runway, the throttle should be closed and the WSC aircraft set to the best glide speed. The point at which the throttle is closed is the downwind key position. The turn from the downwind leg to the base leg should be a uniform turn with a medium or slightly steeper bank. The degree of bank and amount of this initial turn depends upon the glide angle of the aircraft and the velocity of the wind. Again, the base leg should be positioned as needed for the altitude or wind condition. Position the base leg to conserve or dissipate altitude to reach the desired landing spot. The turn onto the base leg should be made at an altitude high enough and close enough to permit the aircraft to glide to what would normally be the base key position in a 90 degrees power-off approach. Although the key position is important, it must not be overemphasized or considered as a phi-crossed point on the ground. Many inexperienced pilots have the false understanding of it as a particular landmark, such as a tree, crossroad, or other visual reference to be reached at a certain altitude. This leaves the pilot at a total loss anytime such objects are not present. Both altitude and geographical location should be varied as much as practical to eliminate any such conception. After reaching the base key position, the approach and landing are the same as in the 90 degrees power-off approach. 360 degrees power-off approach. The 360 degrees power-off approach is one in which the aircraft glides through a 360 degrees change of direction to the preselected landing spot. The entire pattern is designed to be circular, but the turn may be shallowed, steepened, or discontinued at any point to adjust the accuracy of the FL-ight path. The 360 degrees approach is started from a position over the approach end of the landing runway or slightly to the side of it, with the aircraft headed in the proposed landing direction. Figure 1134, it is usually initiated from approximately 2,000 feet or more above the ground, where the wind may vary significantly from that at lower altitudes. This must be taken into account when maneuvering the aircraft to a point from which a 90 degrees or 180 degrees power-off approach can be completed. After the throttle is closed over the intended point of landing, the proper glide speed should immediately be established and a medium bank turn made in the desired direction to arrive at the downwind reference position opposite the intended landing spot. The altitude at the downwind reference position should be approximately 1,000 feet above the ground. After reaching that point, the turn should be continued to arrive at a base leg key position. The angle of bank can be varied as needed throughout the pattern to correct for wind conditions and to align the aircraft with the final approach. The turn to final should be completed at a minimum altitude of 300 feet above the terrain. Common errors in the performance of power-off accuracy approaches include: downwind leg too far from the runway/landing area, overextension of downwind leg resulting from tailwind, inadequate compensation for wind drift on base leg, attempting to stretch the glide during undershoot, forcing the aircraft onto the runway in order to avoid overshooting the designated landing spot. Emergency approaches and landings, simulated engine out. From time to time on dual FL-ights, the instructor should give surprise simulated emergency landings by retarding the throttle and calling simulated emergency landing. The objective of these simulated emergency landings is to develop pilot accuracy, judgment, planning, procedures, and confidence. When the instructor calls simulated emergency landing, the pilot should immediately establish the best glide speed and the aircraft trimmed, if so equipped, to maintain that speed. A constant gliding speed should initially be maintained because variations of gliding speed nullify all attempts at accuracy and judgment of gliding distance in the landing spot. The many variables, such as altitude, obstruction, wind direction, landing surface and gradient, and landing distance requirements of the aircraft determine the pattern and approach procedures to use. Utilizing any combination of normal gliding maneuvers, from wings level to steep turns, the pilot should eventually arrive at the normal reference position at a normal traffic pattern altitude for the selected landing area. From this point on, the approach is as nearly as possible a normal power-off approach as described previously in the power-off accuracy approaches section. Steep approach techniques may be used for faa-h approach if required. If the student is high above the desired emergency landing area, large low-banked circles above the area should be made and widened or narrowed as required to provide downwind and faa-h reference points for the landing. Figure 1135, despite the greater choice of fields afforded by higher altitudes, the inexperienced pilot may be inclined to delay making a decision and, despite considerable altitude in which to maneuver, errors in maneuvering and estimation of glide distance may develop. All pilots should learn to determine the wind direction and estimate its speed from any means available. This could be a feel of the wind drift on the WSE, GPS ground speed versus true airspeed, and visual indicators such as the windsocket. The airport, smoke from factories or houses, dust, faa-h, FLAGs, ripples on water surfaces, and windmills. Once a faa-h has been selected, the student pilot should always be required to indicate it to the instructor. Normally, the student should be required to plan an FLY pattern for landing on the faa-h faa-rst elected until the instructor terminates the simulated emergency landing. This gives the instructor an opportunity to explain and correct any errors. It also gives the student an opportunity to see the results of the errors. However, if the student realizes during the approach that a poor faa-h has been selected, one that would obviously result in disaster if a landing were to be made, and there's a more advantageous faa-h within gliding distance, a change to the better faa-h should be permitted. The hazards involved in these last-minute decisions, such as excessive maneuvering at very low altitudes, should be thoroughly explained by the instructor. Steep approaches, varying the position of the base leg, and varying the turn onto faa-h approach should be stressed as ways of correcting for misjudgment of altitude and glide angle. Eagerness to get down is one of the most common faults of inexperienced pilots during simulated emergency landings. In giving way to this, they forget about speed and arrive at the edge of the faa-h with too much speed to permit a safe landing. Too much speed may be just as dangerous as too little. It results in excessive FL-oating and overshooting the desired landing spot. It should be impressed on the students that they cannot dive at a faa-h and expect to land on it if it is short. During all simulated emergency landings, the engine should be kept warm and cleared. During a simulated emergency landing, the student should have control of the foot throttle and the instructor should have control of a second throttle. The instructor should tell the student to increase the throttle when needed, but the instructor should be ready with the second throttle in case the student does not apply it as required. Every simulated emergency landing approach should be terminated as soon as it can be determined whether a safe landing could have been made. In no case should it be continued to a point where it creates an undue hazard or an annoyance to persons or property on the ground. In addition to FL-ing the aircraft from the point of simulated engine failure to where a reasonable safe landing could be made, the student should also be taught certain emergency FL-ight deck procedures. The habit of performing these FL-ight deck procedures should be developed to such an extent that, when an engine failure actually occurs, the student checks the critical items that would be necessary to get the engine operating again while selecting a faa-h and planning an approach. Combining the two operations, accomplishing emergency procedures and planning and flying the approach, is difficult for the student during early training and emergency landings. There are definite steps and procedures to be followed in a simulated emergency landing. Although they may differ somewhat from the procedures used in an actual emergency, they should be learned thoroughly by the student and each step called out to the instructor. The use of a checklist is strongly recommended. Most aircraft manufacturers provide a checklist of the appropriate items. Critical items to be checked should include the quantity of fuel and the position of the magneto switch. Many actual emergency landings could have been prevented if the pilots had developed the habit of checking these critical items during FL-ight training to the extent that it carried over into later FL-ing. Faulty approaches and landings. Low final approach when the base leg is too low, insufficient power is used, or the velocity of the wind is misjudged, sufficient altitude may be lost, which causes the aircraft to be well below the proper faa-h approach path. In such a situation, the pilot would need to apply considerable power to maintain or gain altitude as required to FLY the aircraft, at an excessively low altitude, up to the runway threshold. When the proper approach path has been intercepted, the correct approach attitude should be re-established, the power reduced, and a stabilized approach maintained. Figure 1136, do not increase the pitch attitude without increasing the power since the aircraft decelerates rapidly and may approach the critical OA and stall. If there is any doubt about the approach being safely completed, It is advisable to execute an immediate go-around. High final approach. When the final approach is too high, perform a steep approach as required for the height above the landing spot. Refer to the steep approach section earlier in this chapter. Slow final approach. When the aircraft is FLO'd at slower than normal airspeed on the final approach, pilot determination of the rate of sink, descent, and the height of roundout is difficult. During an excessively slow approach, the wing is operating near the critical OA and, depending on the pitch attitude changes and control usage, the aircraft may stall or sink rapidly and contact the ground with a hard impact. Whenever a low-speed approach is noted, the pilot should apply power and accelerate the aircraft to reduce the sink rate to prevent a stall. This should be done while still at a high enough altitude to re-establish the correct approach airspeed and attitude. If too slow and too low, it is best to execute a go-around. Use of power can be used if required during the approach and roundout to compensate for errors in judgment. The pilot should be ready to use the foot throttle while managing the energy throughout the landing, utilizing energy management procedures for the current landing conditions. Power can be added to reduce the descent rate if needed, thus, the descent can be slowed to an acceptable rate. After the aircraft has touched down, it is necessary to close the throttle to remove additional thrust and lift, allowing the aircraft to stay on the ground. High roundout. Sometimes when the aircraft appears to stop moving downward temporarily, the roundout has been made too rapidly and the aircraft is FL-ing level, too high and too slow above the runway. Continuing the roundout would further reduce the airspeed, resulting in an increase in OA to the critical angle. This would result in the aircraft stalling and dropping hard onto the runway. To prevent the hard drop, pitch attitude should be reduced slightly to increase speed to approach speed while throttle is added to maintain altitude. After speed has been increased and altitude maintained, the throttle and speed can both be reduced smoothly and gradually for a gradual descent with a normal roundout and touchdown. Although speed is needed after the high roundout is noticed in order to be corrected, the power application must be enough to remain level and not initially descend as the speed is increased. Energy management proficiency is critical. If too little throttle is added, the momentary decrease in lift that would result from lowering the nose and decreasing the OA may be so great that the aircraft might contact the ground with the nosewheel faa-h-8083-5, which could then collapse. As for all landing maneuvers that are questionable and the outcome is uncertain, it is recommended that a go-around be executed. Late or rapid roundout. Starting the roundout too late or pushing the control forward too rapidly to prevent the aircraft from touching down prematurely balloons the aircraft up above the runway. Suddenly increasing the OA and stalling the aircraft during a roundout is a dangerous situation since it may cause the aircraft to land extremely hard on the main landing gear and then bounce back into the air. Recovery from this situation requires prompt and positive application of power and a lowering of the nose to increase speed prior to occurrence of the stall. This may be followed by a normal landing, if sufficient runway is available, similar to the high roundout discussed above, otherwise the pilot should immediately execute a go-around. Floating during roundout. If the airspeed on final approach is excessive, it usually results in the aircraft FL-loading and ground effect. This is not a problem if there is plenty of runway and if the pilot FL-loads with the wheels just inches above the surface. Simply maintain this position inches above the runway, slowly rounding out as required until the speed bleeds off for a normal touchdown. If conditions are turbulent, the nose can be lowered gradually and the aircraft FL-on onto the ground, as discussed earlier in the landing and turbulence procedures. If the aircraft is well past the desired landing point and the available runway is insufficient, perform a go-around immediately. Ballooning during roundout. If the pilot misjudges the rate of sink during a landing and thinks the aircraft is descending faster than it should, there is a tendency to increase the pitch attitude and OA too rapidly. This not only stops the descent, but actually starts the aircraft climbing. This climbing during the roundout is known as ballooning. Ballooning can be dangerous because the height above the ground is increasing and the aircraft may be rapidly approaching a stall. The altitude gained in each instance depends on the airspeed or the speed with which the pitch attitude is increased. When ballooning is slight, the nose should be lowered to increase speed and return to a gradual descent. Recovery procedures are similar to those for rounding out too high, lowering the nose slightly and increasing the throttle to remain level. Then, the pilot gradually reduces throttle and speed for a controlled descent rate with the throttle at idle during touchdown. When ballooning is excessive, it is best to execute a go-around immediately. Do not attempt to salvage the landing. Full power must be applied and the nose lowered before the aircraft enters a stalled condition. The pilot must be extremely cautious of ballooning when there is a crosswind present because the crosswind correction may be inadvertently released or it may become inadequate. Because of the lower airspeed after ballooning, the crosswind affects the aircraft more. Consequently, crabbing has to be increased to compensate for the increased drift. It is imperative that the pilot makes certain that directional control is maintained. If there is any doubt, or the aircraft starts to drift, execute a go-around. Bouncing during touchdown when the aircraft contacts the ground with a sharp impact is the result of an improper attitude or an excessive rate of sink. It can bounce back into the air. The severity of the bounce depends on the airspeed at the moment of contact and the rebound attitude the WSC aircraft. It can increase the OA and, in addition to bouncing, be lifted. It can rebound in a yaw condition and or nose up or down. Design and situational factors create their own unique scenarios. The corrective action for a bounce is the same as for ballooning and similarly depends on its severity. When the bounce is very slight and there is not an extreme change in the aircraft's pitch attitude, a follow-up landing may be executed by applying specific power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. Extreme caution and attention must be exercised any time a bounce occurs, but particularly when there is a crosswind. During the bounce, the wind causes the aircraft to roll with the wind, thus exposing even more surface to the crosswind and drifting the aircraft more rapidly. When a bounce is severe, the safest procedure is to execute a go-around immediately. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. The go-around procedure should be continued even though the aircraft may descend and another bounce may be encountered. It would be extremely foolish to attempt a landing from a bad bounce since airspeed diminishes very rapidly in the nose-high attitude, and a stall may occur before a subsequent touchdown could be made. Porpoising in a bounce landing that is improperly recovered, the aircraft comes in nose faa-h-8083-5, setting off a series of motions that imitate the jumps and dives of a porpoise, hence the name. The problem is improper aircraft attitude at touchdown, sometimes caused by inattention, not knowing where the ground is, or forcing the aircraft onto the runway at an exceedingly high descent rate. Porpoising can also be caused by improper airspeed control. Usually, if an approach is too fast, the aircraft floats and the pilot tries to force it on the runway when the aircraft still tends to fly. A gust of wind, a bump in the runway, or even a slight push on the control bar sends the aircraft aloft again. The corrective action for a porpoise is the same as for a bounce, and similarly depends on its severity. When it is very slight with no extreme change in the aircraft's pitch attitude, a follow-up landing may be executed by applying specific power to cushion the subsequent touchdown, and smoothly adjusting the pitch to the proper touchdown attitude. When a porpoise is severe, the safest procedure is to execute an immediate go-around. In a severe porpoise, the aircraft's pitch oscillations can become progressively worse until the aircraft strikes the runway nose faa-h-8083 with specific force to collapse the nose gear. Pilot attempts to correct a severe porpoise with ight control and power inputs will most likely be untimely and out of sequence with the oscillations, only making the situation worse. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. Wing rising after touchdown in all the proper landing techniques except the soft faa-eld, the nose is lowered after the front wheel touches to put a negative O on the wing and keep the WSC aircraft on the ground. However, there may be instances when landing in a crosswind that a wing wants to rise during the after landing roll. This may occur whether or not there is a loss of directional control depending on the amount of crosswind and the degree of corrective action. Anytime an aircraft is rolling on the ground in a crosswind condition, the upwind wing is receiving a greater force from the wind than the downwind wing. This causes a lift differential. Also, as the upwind wing rises, there is an increase in the OA which increases lift on the upwind wing rolling the aircraft downwind. When the effects of these two factors are great enough, the upwind wing may rise even though directional control is maintained. If no correction is applied, it is possible that the upwind wing rises sufficiently to cause the downwind wing to strike the ground. In a crosswind, the windward wing should be lowered slightly as a preventive measure to avoid it from lifting. But in the event a wing starts to rise during the landing roll, the pilot should immediately lower the nose while lowering the wing. The wing should be lowered as soon as possible. The further a wing is allowed to rise before taking corrective action, the more wing surface is exposed to the force of the crosswind. Hard landing: when the aircraft contacts the ground during landings, its vertical speed is instantly reduced to zero. Unless provisions are made to slow this vertical speed and cushion the impact of touchdown, the force of contact with the ground may be so great it could cause structural damage to the aircraft. The purpose of pneumatic tires, shock-absorbing landing gears, and other devices is to cushion the impact and to increase the time in which the aircraft's vertical descent is stopped. The importance of this cushion may be understood from the computation that a 6-inch free fall on landing is roughly equal to a descent of 340 feet per minute. Within a fraction of a second, the aircraft must be slowed from this rate of vertical descent to zero without damage. During this time, the landing gear together with some aid from the lift of the wings must supply whatever force is needed to counteract the force of the aircraft's inertia and weight. The lift decreases rapidly as the aircraft's forward speed is decreased and the force on the landing gear increases by the impact of touchdown. When the descent stops, the lift is almost zero, leaving only the landing gear to carry both aircraft weight and inertia force. The load imposed at the instant of touchdown may easily be 3 or 4 times the actual weight of the aircraft, depending on the severity of contact. After a hard landing, the WSC carriage and wings should be inspected by qualified personnel for airworthiness. Chapter summary: all landings should consist of evaluating the wind and conditions so a proper base and faa-h are planned to land at or beyond the intended point. After the faa-h approach to the runway, the roundout is started about 10 to 15 feet high and is a gradual descent until the rear wheels are inches above the surface. The rotation is continued as the speed bleeds off to maintain the wheels 1 to 2 inches above the runway until minimum controlled airspeed, at which the WSC aircraft settles to the ground. A roundout that is too fast, or ballooning where altitude is gained during the landing, is a common mistake and should be avoided. The best landing technique for light wind conditions is with power brought to idle during the downwind leg of the pattern before the turn to base. Proficiency and power off accuracy landings with 90 degrees turns, 180 degrees turns, 360 degrees turns, and circling from above are all important safety procedures. Crosswinds or landing in turbulence requires more energy, including power on approaches with higher airspeeds. In these conditions, the WSC aircraft can be flown into the ground above the stall speed. Go-arounds are normal procedures and should be performed if there's any question as to the successful outcome of any landing.